size 1101. This is lab one on measurement. And motion. And what I do here is explain this lab, do this lab. We have 3 different samples. We have a steel sample, which is number 1. We have an aluminum sample, which is number 2. It's number 2. And then we have a brass sample, which is number 3. So we're going to look at on the metal triangle, metal rectangle. So we're going to be dealing with the 3 sample things there. So if we have this aluminum cube, all right, so volume for cube is length times width times height. And if you're in centimeters, this will be in centimeters cubed. All right, so whatever unit you're using, this will be the units for that. All right, we don't have a sphere, which we're not going to be doing today. All right, a sphere like this, the diameter of the sphere, right, you can measure the diameter easily. Right, using this little inexpensive vernier slide measure. And so if you measure the diameter, right, the diameter is say 1.0 centimeters, and the radius is half of that, which would be 0.5 centimeters. 0.5 centimeters, right? Then the volume is going to be 4/3 pi r cubed, right? So if you measure the volume, so make sure if you're doing volume, if you have the diameter, the radius is half that. So it's easy to measure the diameter of it and get it from there. All right, now, that's the first part there. The ones we're really going to be dealing with is with the cylinders. And for the cylinder, and all 3 are the same size. And for a cylinder, the volume is the length, which is this length here, times the area of either surface. So it's going to be length times pi r squared, again, where r is the diameter. So this is diameter, the radius is half of that. So I'm going to do that and write those down, and then doing a couple examples of how we can do our numbers here. So if I measure the length, any of them, measure the length. Now this thing, these are accurate to about, well, 1/10 of a centimeter or 1/2 a centimeter. So what we can do here is this one, the line right here, is 5.0 centimeters. So this is 5.0 centimeters is the length. The diameter of this thing, as I can show, is, looking at here, it's about halfway between 3.1 and 3.2. So I'll call it halfway in between. 3.15 centimeters is the diameter. All right, so approximately can round this up to 3.2 centimeters. So then the radius is half of that, or 1.6 centimeters. Now, we have two significant, so this is two significant figures. This is two significant figures. So when we calculate the volume, so our answer can only have two significant figures, right? I mean, if each measurement is two significant figures, you can't have a volume. So if you have an answer, so because pi is 3.14, so if you multiply this all out, we'll get a certain volume, but it won't be that. So our answer can only have two significant figures, right? So from there, then we have the density, Greek letter rho, is mass over volume. So you can see if all three of these have the same volume, then the mass, the intensity is proportional to the mass. So as whichever one has the largest mass will have the largest density, and vice versa. Whichever object has the highest density will have the greatest mass. So those are the numbers there as far as that's concerned. All right, so all right, so that's part of the questions there are dealing with that. All right, so that's the part dealing with mass and volume. What I'll do now is go on to the short answer questions. All right, first one deals with the Lufthansa flight. And if you look at the question, watch the angle. So the thing will be coming at you. The video will show it flying towards them. And I'm estimating it to be a speed of about 150 miles per hour. It's about the normal landing speed for a plane. So if it's coming, so the angle is going to be the direction the plane is actually aimed relative to its actual motion. So it's coming like this. In this case, it'd be 0. If it's coming in at an angle like this and this way, that's actually pointed this way, this would be the angle, theta. So this is the angle, so it's coming here, but it's actually pointing that way. And the wind would either be coming, then you can figure out what kind of wind is doing that to create it, right? So you can estimate it. So if it's going straight on, it'd be 0. This is 0 degrees. If it was at 90 degrees, so it's coming this way and actually point, this would be 90. You can have the other direction. So if the wind was coming one direction, the other. So we're talking about here. So this angle would be the same as this angle if it was pointed like so, but all it would mean is that wind is coming from one side or the other. This generally comes from some kind of crosswinds, which are very hard to land in, but not impossible, but that's sometimes you do. So that's the angle there, and then you can estimate the speed, because if this is 150 and say this is 30 degrees, this would be a speed of approximately 70 miles per hour, pushing it back this way. So the wind is pushing it this way, it's going that way, so it actually has to aim like so to be able to do that. So that would be the angle, is approximately 30, and it'd be a wind of approximately 70 degrees, pushing it to the right as you are looking at it. So that's that part there, right? So hopefully that'll work. One thing to keep in mind, the wind is never going to be, I mean, a realistic wind is, unless you're in a tornado or hurricane, is no more than about 70, 80 miles per hour, right? So that's that part there. Part 2, smart car. Right, 2, smart car. If you watch the video, there. You'll see the speed. They'll give you that. I'm not going to give you that part here. So, as an example, if it was 50 miles per hour, so something going 50 miles per hour, and the time is, for a normal crash, is about 0.1 seconds or less. So what we'd have here, if this is the speed, this is not the speed for the smart car, I'm just doing an example, then that's it. So if we want to convert 1 meter per second is 2.24 miles per hour, right? So to convert 50 miles per hour, it's times 1 meter per second over 2.24, which turns out to be roughly, let's see, about 22 meters per second, right? So that would be how fast it's going. Now we're going to see this in chapter 2. The acceleration or deceleration is going to be minus v over change in time, minus change of velocity. So it's going from 50 miles per hour to 0 in 1/10 of a second. So that'd be 0 minus 22 meters per second over 0.1 seconds, which is about 220 meters per second squared. All right, in 0.1 seconds, and we'll see 1g is approximately 10 meters per second squared for gravity. So this would be approximately equal to 220 times 1 over 10 would be about 22 G's for this force here. So this is the example here. Look at the video to actually see what the speed is, and we'll take the speed to be 0.1 second. The video they say 1 second, but I'm not sure where they get that. It's actually much faster than that. Okay, much quicker than that, I should say. All right, and the last question is on the Apollo. All right, if you have something in free fall and it's on Earth, right? So you're going to measure the height, which would be h, and the time for it to fall, t. All right. Now, on Earth, g is about 10 meters per second squared, 9.8 meters per second squared. All right. So what we're going to have here for so the way it works then for acceleration is that the distance it falls, h, is 1/2 gt squared. All right. So we'll see from chapter 2, if you drop something and it takes a second for it to land, then that would be 1/2 times 10 times 1 squared, which would be about, let's see, 1 times 10, 5 meters, which is about 16 feet. So an object on Earth to take 1 second, falls about 5 meters, 1.6, 16 feet. So pretty high up. So in this case, we have it on the moon, and I'm not going to go through that. G is not 1 point, it's something else. Right? G on the moon is different. It depends on the mass of the moon, size of the moon, other thing. So in this case, we're going to be given h, because you'll measure that, estimating that. You'll estimate the time it takes. So using the formula, h is 1/2 gt squared, then g eliminate for G. G will be multiply both sides by 2, divide by T squared both sides. G is 2H over T squared. Okay? And where H is in meters, and T is that. So, an average person, so again, 1 meter is about 3.2 feet, 3.3 feet. So 2 meters is about 6.6 feet. 1.5 meters is about 5.1 feet. All right? So you can estimate that based on that so far as that. So it's not meant to be precise, but that's part 3.